Welcome back, everyone. Is me. We're going on a seriously fascinating journey to figure out exactly how the Earth's climate engine actually works. You can kind of think of our atmosphere like, well, like a protective shirt you wear to guard against the elements. It's not just sitting there. It's this incredibly dynamic system that shields us, regulates our temperature, and, literally makes life on Earth possible. So today, we're going to unpack exactly how this massive, constantly moving engine operates. Okay, let's dive into this. Here is the roadmap for our explainer today. We'll start with Earth's protective blanket, then look at atmospheric composition and gases, move up through the layers of the atmosphere, check out pressure belts and winds, and finally wrap it all up with understanding cyclones. Part 1, Earth's protective blanket. So this blanket, it is definitely not just empty space above our heads. It is a constantly moving, highly dynamic shield. Honestly, without this atmospheric envelope, Earth would be a completely barren wasteland. Just imagine standing on Mars for a second. You'd be exposed to literally boiling heat during the day and absolutely freezing cold at night. Our atmosphere regulates this heat budget for us, blocking harmful solar radiation and keeping temperatures perfectly balanced so the biosphere can actually thrive.
Part 2, atmospheric composition and gases.
So what exactly is this shirt made of? Well, a crucial thing to note right off the bat is that the fundamental ingredients, the heavy lifters like water vapor and carbon dioxide, are heavily concentrated in just the first 90 kilometers above the surface. When we break it all down, nitrogen is the undisputed king here, making up 78% of the atmosphere, which is absolutely crucial for agriculture. Coming in a distant second is oxygen at 21%, driving all biological respiration and combustion. Everything else, that makes up just that tiny final 1%. And this brilliantly illustrates that remaining 1%. To remember these trace gases, students in India often use this clever, really memorable Hindi trick, Neha Karti Jimhai. It's a perfect way to recall the descending order of these noble and trace gases. You've got neon, helium, krypton, xenon, and finally hydrogen, which is the absolute rarest gas floating around up there. Now, we really can't talk about atmospheric gases without addressing ozone, right? It actually plays two wildly different roles depending on where it hangs out. High above us in the stratosphere, that's the good ozone. That's our life-saving shield against harmful UV rays, the layer famously protected by the Montreal Protocol. But down here on the surface, in the troposphere, we actually create bad ozone. When nitrous oxide from cars and fertilizers reacts with sunlight, bam, it creates a harmful pollutant that causes smog and respiratory health issues. But hey, the atmosphere isn't purely gas. It's also packed with particulate matter. These microscopic suspended particles, stuff like dust, pollen, sea salt, volcanic ash, and soot, are incredibly important. They aren't just airborne dirt. They act as what scientists call hygroscopic nuclei. Basically, they serve as tiny magnetic centers that gather water vapor around themselves to eventually form rain clouds. Now, what's really interesting about this is how this exact scientific concept was recently put to the test in the real world. To combat severe pollution, the Delhi government actually attempted an artificial rain experiment. They dispersed tiny particles into the sky to act as those nuclei, hoping to force cloud formation. But the project failed. Why? For one very simple reason. There just wasn't enough natural moisture in the atmosphere to gather around those particles.
Okay, moving right along. Part 3. Layers of the atmosphere.
Let's move up and see how this builds. We're going to travel vertically, straight up from the Earth's surface to the edge of space, and watch how the physical rules completely change. We start in the troposphere, where literally all our weather happens. And get this layer actually bulges up to about 18 kilometers at the equator, because intense solar heat causes massive upward convection. Next up is the calm stratosphere, home to our good ozone. Keep going, and you hit the mesosphere, where meteors burn up. Then the thermosphere, which is crucial for bouncing radio waves and hosting our satellites, and finally the exosphere, which just kind of fades out into outer space. Right around the 100-kilometer mark, there is this fascinating invisible boundary known as the Kármán line. Below this line is the homeosphere, where the mix of atmospheric gases is remarkably same, uniform and well-mixed. But cross that boundary into the heterosphere above, and the gases actually separate out into distinct, stratified layers based on their atomic weight. It's quite literally a dividing line in the sky.
Part 4, pressure belts and winds.
So, all these layers and gases we just talked about, they are constantly being heated unevenly by the sun. This temperature difference creates pressure, which puts our entire protective blanket into constant motion.
Across our globe, this uneven heating maps out exactly 7 distinct pressure belts. They alternate systematically: equatorial lows, subtropical highs, subpolar lows, and polar highs. These belts are essentially the grand gears turning the Earth's climate engine.
So the crucial point here is that wind is simply the atmosphere desperately trying to balance itself out. It always rushes horizontally from high pressure to low pressure areas. Down on the ground, friction from things like mountains and trees slows it down. But if you go 2 to 3 kilometers straight up, there's zero surface terrain to block it. Up there, the winds rush so incredibly fast that the Earth's rotation actually deflects them, creating these geostrophic winds that flow perfectly parallel to the pressure lines. And finally, part 5, understanding cyclones. When you combine intense heat, massive moisture, and extreme wind dynamics, this climate system can go into absolute overdrive. This is highly relevant when we look at the severe weather impacts recently seen in regions like Odisha and Andhra Pradesh. Now, it's really easy to look at a cyclone and just see pure chaos, but it's actually a highly structured thermal engine. So what is the exact physical recipe required to birth these massive destructive storm systems? A tropical cyclone follows a very rigorous chronological 5-step sequence. First off, intense ocean heat establishes a deep, low-pressure center. Second, massive convection begins, drawing moist air rapidly upward. Third, as this water vapor condenses into clouds, it releases latent heat, and this acts as the literal fuel feeding the storm. Fourth, those rushing winds begin to spin, developing massive spiral bands. And finally, the storm becomes so intense it actually clears out the center, forming that eerily calm eye. But here is a truly fascinating geographical quirk. Even with maximum heat and moisture right at the equator, cyclones simply cannot form there. Why? Because the Earth's rotational spin effect, the Coriolis force, is exactly 0 at the equator. Without that spin, the rushing air just can't spiral. But move just a little bit north or south into the subtropics, and that Coriolis force kicks in strong, twisting those winds into monster cyclonic systems. And that brings us to the ultimate question. We've seen just how delicate and interconnected this whole system really is, how heat drives convection, fuels latent heat, and powers these pressure belts. With global warming demonstrably raising short-term sea surface temperatures, we are directly injecting more and more fuel into this dynamic envelope. Are we inadvertently supercharging the Earth's climate engine way beyond its natural limits? It's a critical and honestly sobering question that we absolutely must answer as we look to the future.